Today we're going to take a look at section 2.2, which is defined as the derivative. A lot of what we're going to do in 2.2, at least about half of it, is something you've seen in 2.1. So it's not brand new information to begin with, but a redefining of it in a little bit different way. So first of all, the definition of derivative. So the derivative of a function, f, at the point x equals a, is defined to be, so this is our definition, f prime of a equals the limit as h approaches 0 of f of a plus h minus f of a over h. Does that look familiar? I hope so, because if you did your homework, it should. What does it look like? What did we call this in the last section? That was part of it. So one of the things we called this was the slope of the tangent line. There was something else we called it. Does anybody remember? It is the difference quotient with sort of an additional limit part at the front. That's good for you to recognize. You might have seen that in an algebra course. You should have seen it in a college algebra course. We also talked about this in the last section being velocity. Do you remember that one? At x equals a, you'll see that the a here is what's plugged in, so that's why it's x equal to a. And this works provided, excuse me, that the limit exists. And if the limit does exist, we call this function f differentiable. Now, pay attention to the notation. Do you see this over here? It says f prime of a. So that's the notation that we're going to adopt. We'll discuss another notation. I can't remember if it's in this lesson or a different one. There's a couple of other notations that we will encounter that we'll use, but this is the one that we're encountering first, f prime of a. So f prime of a means derivative. Okay. Now I know a number of you have had some form of calculus before, and you know shortcuts for finding derivatives. Just hold on tight. I promise we're getting there. Section 3. All right, section 3. So you have one more section of doing things with limits, all right? But you do have an advantage, right? Because you know some shortcuts to verify your answers, right? Edgar, we were talking about that in my office this morning, weren't we? So you do have that advantage. You can still verify your answers from that perspective. All right, there's an alternate definition. It's not that much different, but an alternate definition of derivative says that the derivative of the function f is the function f prime, given by f prime of x equals the limit as h approaches 0 of f of x plus h minus f of x over h. Just looking at that formula compared to the formula, if you will, on the previous slide, what's the only difference you see? Yeah, instead of a's, there's an x, right? That's all the notation looks like different. They're actually defining this a little bit differently. This is the definition of derivative on its entire domain. So this is the domain of f. So any x value that this would work for, you're allowed to use. I'll promise I'll come back to the slide just a second. Over here, they were defining it at a specific location, x equal to a in the domain. So this is just doing it for the entire domain. That's the only difference, really. The process of finding a derivative is called differentiation. And we also call f differentiable, in this case on an open interval I, if it's differentiable at every point in I. So if, for instance, if it's differentiable between a and b, we would say that f is differentiable on the interval ab, all the points between a and b. And it doesn't have to stop. It could be a to infinity or negative infinity to infinity, those kinds of values as well. Kind of like when we did continuity, right? So we could actually talk about it being differentiable in that sense too. All right. So I think we should try one, because we actually haven't done one together. You guys watched a video, hopefully, where you were working through some. We haven't done one together in class. All right, so this one says compute the derivative function f prime. So let me just sort of ask the people who have seen calculus before if they know what the answer is so we know where we're headed. This is what you would do if you were looking in the back of the book too, right? What should my answer be, those of you who've seen something of this nature before?
3x squared plus 2.
That is correct. 3x squared plus 2. This is going to be the answer when we're done. And those of you who haven't had calculus are going, wow, that was pretty cool. And you know what? Next class period, you're going to be able to do that too. So, but not yet. So let's take a look at this process. So this process is to do the limit as h approaches 0. We're going to work with it just with the x in there. If you want to put the a in there instead of x, more power to you, that's fine. I'm going to work with x's in there. So the definition says f of x plus h minus f of x over h. That's just me rewriting the definition. I'll write the notation in front, f prime of x, that's what we're finding. This is what we're looking for, right? So we worked last section notating what this is. This is an algebra concept. So when we say f of x plus h, it means take the original function, and everywhere we have an x, what are we going to do? We're going to put in an x plus h. Now every step we do, we're going to rewrite limit until when? Until we actually plug in 0 for h. So please remember your limit notation. I'm definitely not going to have enough space there. Let me move that. Okay, so the first thing to do then, like we said, is to take all of my x's and replace them with x plus h. So this would be x plus h cubed plus 2 times x plus h plus 1. And if you will, this is everything that I've got in blue right now. I know you guys can't see the colors all that well, but it looks a little bit different on the screen. So that's the piece that's in blue. This part right here that's in red at the end is the function I was originally given. So I can actually use that function as already given to me, and I'll put it in brackets as well to clarify which piece I'm working on. So this is x cubed plus 2x plus 1. So those are the two pieces that I'm subtracting, and I'm going to divide this by h. Okay, is everybody good so far? All nice and good? I think you had a problem that was very similar where it was cubed like this at a different point. I'll work it out with you once, but if you will remember the form for it, you don't have to work it out every time. X plus h cubed means you have x plus h times x plus h times x plus h. So this is sort of like scrap paper working out that we're going to do. I'm going to erase it so I'll have more space here in a minute. You take two of them and you multiply them together. So let's take these two and multiply. What happens when I take x plus h times x plus h?
X squared plus 2xh plus h squared.
Excellent. Is everybody good with that step? That's just foiling and combining, right? And then the last one isn't really foiling because we've got a trinomial times a binomial. So we have to do it piecewise. So I'll take the x squared times the x and then the x squared times the h. So that's going to give me x cubed plus x squared h. And then we can take the 2xh times the x and the 2xh times the h. So that's going to give me 2x squared h plus 2xh squared. And then we're going to take the h times the x and the h times the h. So I get h squared x and h cubed. Now parts of this combine, right? Not the x cubed. He's all by his little lonesome. What does combine though? The x squared h and what else? The 2x squared h. There's a couple of them that look exactly the same in terms of their variables, right? Actually, be right next to each other the way we did the problem. So 2 and 1 of these gives me a total of 3. 3x squared h. What was that, Christian?
Should be 3 in front of both squared.
Yeah, it will be 3 and then x squared h, like I wrote at the very bottom. You're right. And then actually the next two match as well, don't they? I've got xh squared or h squared x, just the order's different, but we can change the order because it's commutative. So I've also got 3xh squared, or you can write it h squared x. And then I've got the h cubed. So all that work right there is going to replace the part that I had up here in blue, right there. Okay? So let me use this notation again. Limit h approaches 0 of x cubed plus 3x squared h plus 3xh squared plus h cubed. And all that was this piece right here, the part that I just highlighted. We still have the rest of it too. So I also have what? well, first I've got 2x, right?
Yeah.
And then,
Plus 2h.
yeah, plus 2h and plus 1. And we can distribute the negative through the next part if you'd like. That's fine. Or you can recognize that everything that's in this next part is flat out going to add with something from before. That didn't work out very well. Let me try that again. It's going to add with something before, and it's going to simplify. So I tend to leave this one without the distribution because I recognize that all of those pieces in that side, that last bracket, are going to add with something else to be 0. So take a look. This x cubed is subtracted. Do you see another x cubed at the beginning? Yeah. So this x cubed and the x cubed at the end, those are going to add to 0. And the same thing happens with the next term. The next term is a 2x, and it's subtracted. And then there is a 2x here. So those add to 0. And then the last term, which is a plus 1, which is subtracted, also has a plus 1 in the first brackets. So those add to 0. So everything in that last bracket set here adds to 0 with something else from before. And we don't want to forget this piece. This is all written over the denominator h. Okay, everybody good so far? Excellent. I had some in my office this morning, and they asked me, what happens if everything on top doesn't have an h in it? And then my answer is, Dean, I think it was you that I said it to. What was my answer? Then you did something wrong. Everything in the numerator has to have an h in it when it's all simplified. It has to. If you didn't have that happen, you did something wrong. You made a mistake somewhere. So it's a really good indicator to go back and relook at your work and figure out where you made a mistake. Now on ours, everything does have an h in it, right? I've got 3x squared h, I've got 3xh squared, I've got an h cubed, and I've got a 2h. Everybody good so far? I'm going to encourage you to factor the h out of the numerator instead of just reducing it. Some of you will probably be just fine with canceling it, and some of you are not going to be quite so fine with canceling it because you're going to lose something. So if I factor an h out, I've got 3x squared plus 3xh plus an h squared, and then plus 2. Everything gets factored an h out of it, all divided by h. Then what happens? Yeah, we have a beautiful cancellation here, which is what we were striving for all the way along. That's the goal. We have to get that h in that denominator to reduce with something in the numerator. Why?
Because it's undefined with 0 at the bottom.
Right. We cannot let h be 0 as long as that h is in the denominator. So our goal is to very much, in fact, get that h to reduce with the numerator. And we had that happen, so that's fantastic. So now we are at the point where the limit as h approaches 0 is of the function 3x squared plus 3xh plus h squared plus 2. Now, is it possible to actually plug 0 in for h? Absolutely is. And if I do that, what will I get? 2. Now take a moment and take a look. This said to compute the derivative function f prime. What did we do? Oh wait, no, sorry. You guys missed one. Sorry, I was overlooking it too. There's a 3x squared in there. Perfect. Get the first part. There's only an h left in this piece and this piece. There we go. And then the plus 2. Good. And back up at the beginning, is that what we said it was going to be? I think it is. So we got it. And so there's my derivative. I'll mark it here at the end too for our solution. Now what if it said that it wanted the derivative at a specific value? Like it wanted to know, find the derivative function, instead of it just saying find f prime, it wanted to find f prime of, say, 4. Yeah, you would plug the 4 into the very last location. That's the simplest way to do that at that point, because you've already done all the work with x in there generally. Now you can just plug in x as the value 4 at the end. All right, any questions on that one? Great. We are going to do number 2. This should hopefully help out several of you who on the test did not do so well on problem number 3. So if that's you, problem number 3 from your test, take particular note to what we're doing, because the process that we're doing on this problem will help you out on that problem as you're reworking your test problems, okay? All right, so this says to compute the derivative function, f prime, but this function is not a polynomial. So some of you who've had calculus, maybe in the more distant past, might not even be able to look at this one and tell me for sure what the derivative is. If you've had a fair bit of calculus recently, you might be able to, okay? So I'm not going to put any of you on the spot to tell me what the derivative is on this one, because this one's more complicated. And you won't be able to do this one in the next section of material either. It's going to be a couple sections down the road before we can work on this one. I think it's in 2.4 or 2.5. All right, so that said, let's take a look. The process is all still the same. We're going to do the same thing. So I'm going to write an f prime of x. This is going to equal f of, whoops, I missed my limit. Let me get that in there. The limit, as h approaches 0, of f of x plus h minus f of x over h. Do you have to write that every time? No, you don't have to write that part. But for now, I'm doing it to remind you which pieces we're plugging in from where. All right, so this piece right here is f of x plus h. And I want my function that I was originally given with the x replaced by x plus h, right? So it's still going to look like a square root. It's still going to have a 4 in it. But where it originally had an x, it's going to have an x plus h. And that is in parentheses beside the 4. It is going to both of those pieces will be multiplied by the 4. And then there is a minus 2 underneath that radical as well. So this right here was the first part in blue. Now the second piece, minus f of x, is the piece that you don't really have to work to find. It's the exact equation you were originally given, f of x. So we can replace that with the function we were given, 4x minus 2. So this piece is the red piece. And all of this needs to be over h. Don't lose that along the way. It's important. All right, so let me actually rewrite this, just a very quick rewrite, and then we'll talk about how this applies to the problem from your exam. So this is 4x plus 4h minus 2, and then minus the square root of 4x minus 2 over h. All right, so this looks a lot like your exam problem. It's a little bit more complicated, actually, because I have two radicals. But otherwise, it looks the same. I've got a radical minus something or plus something, and it's over the h, and the h in the denominator is exactly what's causing quote-unquote problems for us. Right? We got to get that h in the denominator to go away. So what we need to do is we need to do something called rationalizing. So for those of you who did trig last semester, and I know that was a number of you, most of the time in trig you're rationalizing denominators. Well, that's fine, but we can rationalize the numerators as well. So we did this back in section 2 or 3 of the last chapter when we rationalized. And to rationalize, we multiply by what we already have with the radical form, but you change the sign in the middle, and we call that the conjugate. So we're going to take what's currently in our numerator, and we're going to create the conjugate for that. So the conjugate looks exactly like the radical form I already have, so 4x plus 4h minus 2 under a radical. I change the sign between, in this case, between my radicals, and the second radical looks exactly alike as well. So the only thing that's different when I do this is the sign between the radicals. Everything else is exactly alike. And if I do this to the numerator, what do I have to do? I have to do it to the denominator as well. I know it looks really messy, but things are about to clean up very quickly. So just bear with the mess for a few more moments, and stuff will start to eliminate itself by adding to 0. Now, the whole reason that we did the conjugate was because when we multiply out that numerator, there will be no more radicals. And we created it, the reason we chose the conjugate to do that is because when we do it, it's a difference of squares. The first two pieces get multiplied, radical gets eliminated. The last two pieces get multiplied, radical gets eliminated. And when we do the inside terms and the outside terms, they're exactly the same, except one's positive and the other's negative. So they add to 0. So what happens is this is the form that you've seen before that says something like this. A plus B times A minus B, this is what's called the difference of squares, is going to be A squared minus B squared. the middle terms get eliminated, right? Because this one is positive AB and this one is negative AB. So that's what we're doing, but we're doing it with radicals in this particular problem. So we're going to take what we have and we can, in essence, eliminate radicals then. So we're going to get, the first part was 4x plus 4h minus 2. Because that's what happens when I multiply the first radical in each set of parentheses together. I don't have an inside or an outside term, so then I multiply the last together. Well, it's a negative because one's positive, the other's negative. And then when I multiply the square root of 4x minus 2 by itself, I get the same thing, but with no square root. And so I have this beautiful thing that has no radicals in it now. Unfortunately, the denominator still has radicals. So we're not actually going to multiply the denominator out. That would be unhelpful for what we're working with. So we're going to leave it beside the h, just like it sort of already is. But we're going to write it as a multiplication factor. Oh, that wasn't what I wanted to do. The denominator stays looking just like it did before, not factor or not distributed out or anything, just as messy as it did before. But notice what happens in the numerator. Things disappear. Somebody tell me one thing that disappears.
4x.
4x. Matt, why does the 4x disappear?
Because with the minus in between, it makes the second 4x a minus 4x.
Right, so the first 4x is positive, the second 4x is subtracted away with the negative in between, so these add to 0. Somebody tell me something else that goes away. The 2's, and for the same reason, right? Yeah. So this is minus 2, and the next one is minus a negative 2, or is negative 2 and then minus a negative 2. So what is actually left in the numerator? 4h, and that's actually really good. It sounds like we're talking about livestock, 4h. So we have 4h on top. We have this h, square root of 4x plus 4h minus 2, plus the square root of 4x minus 2 on bottom. Now what? You can cancel the h's. I've got a numerator that says 4h, and I've got a factor in the denominator that's h. So these two h's divide, right? They reduce to the value of 1. So I end up with, do I have space here? Well, I'll use this space for a moment. Ignore this part right here. We're just going to continue the problem from the slide before for a moment. So from the slide before now, I have a 4 on top. And I have the square root of 4x plus 4h minus 2. What was it, minus plus? Plus the square root of 4x minus 2 on bottom. Does that look okay? That's all I have left? Okay, now what? Yeah. So the last step is to plug in the 0 for the h. Why do I know that I'm actually ready to do that finally? Yes, because I eliminated the problem that made the denominator 0. When I eliminated that h, I eliminated that problem. Okay, good. So now I can let h be 0. And if I do that, I end up with 4 on top. And then I have the square root of the 4x minus 2 plus the square root of 4x minus 2 on bottom. That's 2 of them, right? Yeah, so we can add those together. They look exactly the same. And so I can actually write this as 4 over 2 square root of 4x minus 2. There's one more thing I can do.
4 and 2.
Yeah, this 4 and this 2 would reduce to a 2 on top. So my derivative ends up being 2 over the square root of 4x minus 2. Now, I usually have someone at this point ask me a question. So are you guys going to ask me a question about this? No, it is. It's the answer. It is correct.
You want us to leave a radical?
That's the, you got it, Tristan. Do you want us to leave a radical in the denominator? And the answer is yes. And you want to know why? When you did this in trig and you rationalized the denominator, you had numbers in the denominator. Do you remember that? You had things like square root of 2 or square root of 3 in denominators, and you rationalized. The problem is you have no idea what this value for x is because it changes, which means that in some cases this already is a rational number. So when we're working with functions, we don't worry about leaving radicals in the denominator. Radicals and denominators are just fine for function notation, okay? So if you've got an x underneath a radical, the function can stay in what appears to be a denominator that's irrational or something like that. So this is perfectly fine. Okay? Does that sound good? All right. Okay, let me go on to this slide then, since I told you we were about to hear the alternate derivative notation. So it was in this particular note set. So this is the one that we did just a minute ago. I said that this is one notation, f prime of x. F of x, as you know, is another notation or another name for the value y. It's a y value, so you see also here we've got a possibility of writing down y prime. Okay, so that's the same thing. Those don't really look a lot different. The next two look quite different, however. The next three look quite different. These notations all look similar to one another. dy dx, df dx, dx dx of f of x. Okay, so these are all notations that mean the same thing. They mean derivative. And if you think about them from the perspective of what we did in the last section for slopes, they have a very good intuitive idea. So somebody tell me what you remember about finding slope. Just plain old college algebra, how do you find a slope of a line? Yeah, so we have the change in y over the change in x. Or you might remember something like y2 minus y1 over x2 minus x1. Take a look at this notation here in the middle. dy over dx. It's got that same feel to it that slope does. And for very good reason. That's what we're finding. We're finding slopes of tangent lines, as we discussed back in section 1. The middle part is just a notation much like the fact that we can call this f prime or y prime. So you've got df dx for the function notation. The last notation is probably the least used notation, but it works just fine. It's saying you have the derivative with respect to x, that's d dx, of the function f of x. Okay? It doesn't really matter to me which one of these notations you use, so you can use what you'd like. However, if in the directions it actually asks you find dy dx, you better know what that notation means. You better recognize and say, oh yeah, this is asking me to find the derivative. So that's more than anything why I presented, is because you should be aware that they all mean find the derivative. Okay? All right. The other thing that we're going to do in this section is we're going to look at sketching graphs. All right? So to start with, I want to kind of give you some ideas about sketching graphs. The goal when we try to sketch a graph of f prime, okay, so in particular we're going to be working with functions where we don't have an equation. That's the idea. We're going to be given a picture of a graph, and we're going to be told, using this graph, give a plausible or possible sketch for its derivative. So the goal is to start with a function and draw a graph that represents its derivative, i.e. its slope, at every point. So in general, what do? Well, in general, we observe what the function's slope is doing. That sounds sort of simple enough. We're going to look at it and say the slope is doing this. But specifically, how do we go through that? Well, there's 3 steps, and the last step says sometimes. Sometimes you don't need it. But in particular, the first thing you're going to do is you're going to look, where is the slope 0? Okay? Where do you have slope values of 0? And you worked a little bit with drawing tangent lines in the last section. So if you think about that, the idea is, where is the tangent line horizontal? Because that's a slope of 0. The second thing to look at is where the slope is either positive or negative. Now sometimes steps 1 and 2 will give you enough information that that's good, you're ready to go. Sometimes it doesn't give you quite enough information to make an educated guess about what would happen next. So when that happens, sometimes you have to note how the slope is changing. That is the slope getting steeper? Is it getting sort of flatter or more shallow? So we're going to be looking at those features for some cases as well. I'll wait while you guys jot those details down. All right, are we good? Almost, Kaylee. Are you still writing? Okay. You good? Okay. All right, so we're going to take some graphs. Please, when you're doing these, it is helpful for me, and it will be helpful, I think, for you, to draw a separate graph instead of drawing them on the same axis. It's not impossible to do on the same axis, but it starts to look a little bit confusing sometimes. So I'm going to ask that you draw it on a separate axis for me. Now, the axis needs to be set up so that it has the same x values that the original graph has. So, for instance, this graph has an x value a and b, and they're on the right-hand side of the graph. So on your graph, you're going to have an a and a b on the right-hand side of the graph, roughly in the same spacing and stuff like that. And we're going to say this then is our function f, and our goal over here is to draw f prime. Now in doing that, we're going to go through the first two, anyway, of those steps back on the previous slide. So the first step is to identify where the slope is 0. So think about drawing those tangent lines like you did in the last section. Slope of 0 means you have a horizontal line. If you were drawing tangent lines, where would you have horizontal tangent lines in this graph? At A and B. Peaks and valleys are usually those places. There are a few other possibilities, but honestly, if you do have peaks and valleys, they will have those slopes of 0. So we're going to write down that our slope is 0 at A and B. What is the second step? Okay, be careful. I don't want to use increasing and decreasing because that actually applies to step 3. What the words did it use on step 2? Positive and negative. So we're going to be very clean and clear, and we're going to use the words positive and negative. So the slope is positive, and we're going to identify where that happens. And the slope is negative, and we're going to identify where that happens. And you'll see why in just a moment that I want to use specifically that language. It'll be much more helpful. So where is this slope positive? If you drew tangent lines, where do you see this slope being positive? Until A. So like this, Christian, does this look okay? From negative infinity, so from the far left side of the graph until I get to A.
And from B to...
And then I sort of skip, right? And I pick back up at B, and I go from B on. Okay, so in particular, I am looking for where the graph's going uphill. I mean, where the graph itself is increasing. But where the graph is increasing is a statement about where the slope is positive. So my slope is positive from negative infinity to A, and then it's positive from B to infinity. Now then, where is the slope negative? Right, from A to B. And when you have enough information, and this is plenty of information, we don't really need step 3 here, okay? Step 3 is going to come into play when we don't get a lot of information out of steps 1 and 2. So here's the next thing to do. If you have a different color pen or pencil than you're currently working with, get it out. If you don't, borrow from the neighbor next to you. Maybe they do. Okay. Everybody's got something, it looks like, or at least access to somebody else who does. All right, good. Here's what you're going to do. Everywhere that you just wrote slope, I wrote it 3 times. I want you to cross it out. And I want you to write y value. Okay, so mine looks like a complete mess on the board, and yours probably will too. It helps with the colors being different on your paper. That's why I suggested the colors being different. So here's why we did that. What we want to do is we want to draw a graph. Our graph is a graph about the slope. But in our graph, it's the y values that are going to do these things now. So the first line is the easiest one to take into consideration. It says, I want the y value to be 0. What does a y value being 0 mean? It's on the x-axis, right? The y value is 0 if you are on the x-axis. And so I'm going to be on the x-axis at A and at B. Those are my x-intercepts. So those 2 points that I just plotted came from step number 1. Now step number 2 talks about the y value being positive. What does it, and negative, what does the y value being positive mean for a graph? Yeah, it's above the x-axis, right? Positive y values are above, negative y values are below. So I should have positive values for the left-hand side before A and for the right-hand side after A. So what's it going to look like? Yeah, on the edges anyway, we know it's going to be looking like a parabola. And notice over here that this graph does indeed cross over into the negative side of the graph, like to the negative. So our graph for our derivative is going to do that as well. We don't want to sort of think that we're trapped inside the first quadrant or something like that with that piece. And then the third line of text that we wrote down says the y value is negative. What is the y value being negative going to mean? Below the x-axis. And all of this needs to be connected and smooth because the original graph was connected and smooth. So I need to connect the two pieces that I have that are pointing upwards to something beneath, so it's actually going to look pretty much like what you said before, which was a parabola. Yeah. So it's going to look something like this. This is a sketch. There's nothing with units or anything here to indicate for you, like scale or anything like that. This is just a sketch. That's all it is. So this is a plausible graph for the derivative based on the information from the original graph. All right, you ready for the next one? Okay. It just so happens the next one is a parabola. It is. And we're going to do the same thing. We're going to first draw the x and y axis. It doesn't actually have anything noted here, like important points, but there's an important point on that parabola. What's the important point that we're going to be referencing? It's not where it crosses the x-axis. It's a good guess, though. It's where the slope is 0, which would be the what of this graph?
Like the low value.
The low value, the minimum value, right? When we're talking about a parabola, if that's what this indeed is, it's called the vertex sometimes too. So it's the minimum value. So it would be helpful for us if we probably give this a name just so that we can reference it. I'll call it A, and then we'll try and put that location over here in about the same place. Okay, you can call it whatever you want, but that way we've got a reference point. It's also going to be helpful because we need it somehow to write down what we're going to write down next. Because the first thing we're supposed to write down is we're supposed to write down where the slope is 0. So the slope is 0 where? At A. We need to have something to call it out. So we're going to say the slope is 0 at A. Next, slope is positive where? Which piece of it? A to infinity. The slope is positive from A to infinity. Positive means that it's going uphill. It's a positive slope. And then what about slope is negative? Yeah, the slope is negative. Whoops. From negative infinity to A. Now, without having an actual equation, there's going to be some variation of what you could draw next. There are some details that are going to have to be the same, but I'm going to draw you a couple of examples of things that could happen based on the details we just wrote down. First thing, though, before we write and do any details, is what are we going to do? We're going to change the word slope. And the word slope is going to become what phrase? Y value. Okay, so now step number 1 is going to look the same on all of your graphs. Step number 1 says I have a y value of 0 at A. What does that mean? It is on the x-axis at A. Perfect. Steps 2 and steps 3, or 2A and 2B, whatever these next two things are, have the potential to look a little bit different on your graphs. There's some feature of them that are going to be the same. The first one says that the y value is positive. So what does it mean for the y value to be positive? Above the x-axis. So my graph needs to be above the x-axis from A on. How that looks on your graph could be different. So I'm going to give you one option for now. Go ahead and draw this option for the moment, and then I'll show you another possibility later. This could actually look like a line. We don't know, but that's definitely a possibility. And then before the value of A, my slope should be negative. So what should that look like? Yeah, below the x-axis. So we'll see if I can draw my line well. Nope, I can't. Let's try again. No, that's not too bad. So it could actually look like a line. That would be an acceptable way to draw this. We aren't told that it has to be a line, though, and we aren't told because we don't know what the original graph was. So it actually could do something like this and curve as well. We don't have anything that says that it can't, so that would be a possibility for this as well. So either of those options would work. Any questions on that one? Okay, so as luck would have it, the next graph is a line. You guys know that this isn't luck, right? We're going to come back to this idea in a later section. All right, so let's take a look at this one. I want you to notice that something's missing that we've always had in the last two examples. What's missing?
A spot where the slope is 0.
Spot where the slope is 0, right? There's no maxes, there's no minimums, right? Now, that's an important feature we're going to actually write down, that the slope is never 0. Okay? So it's not going to be something that's going to be on our graph. In particular, it's something that's going to be sort of blatantly missing from our graph. Step number 2 talks about positive and negative slopes. So what can you tell me about this graph?
It's positive.
Good. The slope is positive. And it's positive everywhere. Okay, so you can write the word everywhere. You could put the interval negative infinity to infinity, whatever you'd like on that. Either of those would be fine. So here's our first place where we're going to invoke step number 3. Step number 3, if you'll remember over here, said to note how the slope is changing. So what can you tell me about that with this graph? How is the slope changing? It doesn't change. What do you know about slopes of lines? They're constant, right? So this slope is constant. Or you could say doesn't change. That would be fine as well. That's all the details we have. So now what are we going to do? Yeah, we're going to rewrite slope as y value. So if I have a y value, if I don't have, basically, a y value that's 0, what does that mean I don't have? If I had a y value of 0, what would I do? I'd cross the x-axis. So for this graph, I don't cross the x-axis. Never going to cross the x-axis. That's what step number 1 tells me. Step number 2 says that the slope is positive. So what does that mean?
That it's above.
Whatever I draw has to stay above the x-axis, right? Because those are the positive y values. The last thing says that the y value is constant. What does it mean for the y value to be constant or for the y value to never change? It's going to be a line that's straight, which is what we mean by line. Try again one more time. Horizontal, that's the word I want. It's going to be horizontal. So we are going to have a horizontal line, I'll do it a different color, somewhere above the x-axis. And we don't have a specific value because we don't have any scale on which to draw this. But it's going to be a line that is going to be horizontal and above the x-axis. Any questions on that one? All right.